So I want to introduce you in this section to the idea of universal approximation of neural networks. The idea behind that is really powerful, that a neural network having just a single layer of some finite size can approximate any function. Okay? So if I have a function here and I want to approximate it, I'm going to create the approximation using my neural network, and I can do that with fidelity of epsilon. Meaning that if I have a lower tolerance for my epsilon, I want it to be more closely approximating f, then I'll need accordingly more units in order to do that. So even though I know that there is a neural network through this proof that can construct that function, let's just have the caveat that it doesn't necessarily mean that I can construct it or recognize it if I have one. Okay? And this universal approximation holds for the topology of a single hidden layer neural network. It actually doesn't depend at all on the activation function that we use. So we're going to show this through a graphical proof. The idea is that we're going to first build a bump function. The bump function just looks like this, right? So it says that it's going to be 0 for all the times where my x1, my univariate input, is varying, except for when it is between two specific goalpost values. Okay? And during that time, it's going to have an activation for a particular value. So what you can see is if I have a higher tolerance for how badly I can approximate my target function, I won't need so many bumps. Like I can just use 3 here. 1, 2, and 3 on the golden ones here. If I have a lower tolerance for how well I'm going to approximate, so I want a good approximation of f, I can use more bumps, right? So as long as I have the capability to manufacture bumps of different width and different height, I can approximate this function as arbitrarily good as I want, right? I could make the rectangles here very, very narrow and make sure the center of each of the rectangles is exactly the target value that is for that value, is exactly the target value. So let's recap how that works for a single univariate input, right? So if I take the logistic function, which is here, what I can say is that it has a function of 2 parts, right? It has a function that's based on the signal, and the signal is composed of both the input as well as the constant bias. So I have 2 parts to tune, my theta, which is due to the weight on the particular input, and my bias, which is constant. And if I set these values, let's say theta equals to 8 and b minus 4, then I'll give this nice smooth logistic function between 1 and 0. When I vary theta and the bias, or theta 0, this is, you can think of this as theta 1, then I'm going to change how this curve looks. For example, if I change my bias to a more negative value, this curve is just going to be shifted to the right, which is what you see here, right? So I'm going to shift it like this, which is exactly the picture that we see here. If instead I increase the value to a positive value from -4 to 0, then I'm going to get a left shift, right? Which is what you see over there. So that was our bias. If I change our weights, we're going to have something different, right? So if I change it down to 0, it's going to be a flat line at the bottom. If I change it to 16, this curve is going to be much, much sharper. Okay? So you can think of this as the weight function is tuning between the linear as well as the step. So if I made this value a very high number, you would see it approaching a step function. So that's what we're going to do. If we use a sigmoid function instead of something like perceptron's step function, we can get a step function by just setting the weight very, very high, okay, and then moving these parameters to make the step occur at a particular point. So if I wanted to occur in the middle here between 0 and 1, I would set my theta equal to 200, my bias equals to 100 to make something that looks very sharp, right? And because 200 divided by minus 100 is 0.5, then I would have it exactly in the middle. So then I can shift this particular step function around by merely tuning the parameters of where I'm going to put the step by changing my bias weight. So if I have a more negative value, it's more shifted to the right. If I have a less negative value, it's more shifted to the left. Now that was one unit. Now I can compute a bump using 2 units at a time, right? I can go compute the front of the bump through one path and compute the back of the bump through another path. So let's look at the center and see how that works, right? I can set the front of the bump equals to 0.4 by using those weights by tuning the bias and theta, and then having a positive activation here for the next layer, right? So 0.4 coming from this unit would turn this one up to a level of 0.4, and then having this neuron fire at 0.6, I'm going to add a minus 0.4 to this. So instead of just going up, I'm going to add a negative 0.4 and I'm going to come back down. So that's going to create this bump function that we need. And I can tune the height of the bump function by just tuning my second layer, right, the output layer here to a different value, right? So I have a 0.4 and negative 0.4 here, and here I have a 0.8 and negative 8 for my output, and here I have a 0.2 and negative 0.2 for a smaller bump, right? So you can see where we're going with this. All I need is this one hidden layer in the middle here that's going to specify when a particular pair of neurons is firing a bump. Okay, so here I have a bump that represents from 0 to 0.2, and then I'm having a value for the top node of negative 0.5, which is going to create this downward bump, okay, and recovering it back to 0 when I get to 0.2, right? So I'm going to add 1.5 to that, okay? So that's going to create this particular golden rectangle here, which is just this bump function that I can draw directly, right? It's going to look a little bit like this, just for the 2 nodes here, right? So I can do this for the rest of the nodes, right? So for example, this pair here is going to create another bump function that looks a little bit like this, and so on and so forth. So with this, you can see that we can approximate any function to an arbitrary level of fidelity that we want by just including more and more pairs of nodes.